Hello, everyone, and welcome to the third in a series of lectures about Chapter 17. Today we'll be covering Section 17.3. So, much like a wave in a pond of water, when a skipping stone hits the surface, sound waves propagate outwards from their source like a ripple. And like any other wave, it's not the medium that gets transferred from one point to the other, but rather energy. And when you think about it, though, our perception of sound is just the wave that we receive where we stand. So you have a long, you have this big ripple that propagates outwards from the sound source, but you as an observer are standing somewhere in the distance, so you only really receive one part of the wavefront continuously. So even though, the entire energy of the wave on average is contained within, this entire series of ripples, we only receive so much of it. Any observer receives only so much of the energy of the wave, depending on where you stand. So rather than talking about the total energy of the wave or the total rate of energy, we'd rather talk about the intensity, where intensity doesn't just account for how much energy the sound wave has, but it also accounts for how it's distributed over some area. Because after all, the further you are from the sound source, the quieter it seems. Or in other words, the closer you are to the sound source, the more intense, the more loud it appears. We perceive things louder when we're closer to them. And that's because when you're closer, you're kind of receiving the full front of the ripple. While you're farther away, the ripple's a lot more expanded out. So you can kind of see this here, where Marty McFly plays a little too close to the giant speaker, so he gets the full front of the sound wave. If he stood farther apart, the sound wave, after a distance, spreads out. You won't get such a strong blast, so don't stand close to speakers. Formally, intensity is the rate of energy transported by a wave through some unit area that's perpendicular to the direction of travel. In other words, it's basically measuring the average power of the wave over a single period, how much power there is over the current size of the ripple as it propagates outwards. And for a sound wave where the power of the sound waves, related to its energy, its density, its speed, and sort of like the way that the particles displace from equilibrium, then you can express that intensity for a sound wave in terms of its density, angular frequency, maximum displacement of equilibrium, and wave speed. Which, by the way, this formula should be reminiscent of the intensity of the power you saw for the wave on a string, where you had, instead of rho, you had a linear density, and instead of the S max, you had the transverse amplitude. And because there's a relationship between the maximum amplitude achieved by the particles and the largest variation in pressure in the medium due to the sound wave, you can also express intensity as a function of the maximum variation in density. The maximum variation in gas pressure. And again, both delta P max and delta S max, and just S max, are analogous to amplitude for transverse waves. And the A here, again, doesn't stand for area, it stands for, it doesn't stand for amplitude, and it stands for unit area. So we'll see what I mean here. And suppose we have a point source producing sound waves. So imagine like a boombox in the center of a room. It basically creates a 3-dimensional ripple. So it's kind of like emitting this, this wavefronts, these continually growing sort of spherical ripples of sound out from it. And they're moving in all directions surrounding it with the same wave speed. It's all the same wave. And in the figure here, we're going to show this, in 2 dimensions, where now we have a source and it's emitting these ripples outwards. And the idea is that the entire wavefront is considered to be a part of the wave that's all in the same phase. So where the wave is all compressed equally and it's all spreading outwards radially, that's one wavefront. And then, right, there's a consecutive order of wavefronts one wavelength away. And you can also draw these rays here that just indicate the general direction of propagation of the wave, which in this case will be all directions. The other side is not shown, but it's really moving in all directions. And if you also want to measure the wavelength, you can. The same way you did in the gas chamber example in one dimension. Now you just need to measure the distance between any two wavefronts. So, right, the distance between any two refractions or two points of maximum compression, those can basically make up the wavefront and measure the distance between any consecutive ones one wavelength apart, and there you go. So then to calculate the intensity of the waves produced from a point source, then you have to talk about the unit area as the area of a sphere, since the wavefronts coming out of the source are essentially ever growing spherical wavefronts. So for the intensity formula, then you have the average power of the wave on top, and on the bottom you have the area of the wavefront, which is equal to, again, the surface area of a sphere, as measured with r being the distance from the source to the current location of the wavefront. In other words, as the wavefronts propagate outwards from the source, they get bigger and bigger, which means then that the total power of the wavefront sort of gets diluted, gets spread out over a bigger area. This is kind of like blowing a bubble with bubble gum, where the bigger you blow the bubble, the thinner the wall of the bubble gets. So within a whole wavefront, the entire the entire energy of the sound wave still contained. It's just that as it expands, the wavefront has a bigger area, and such the power contained in each little slice of that area is a lot smaller than earlier on when the wavefront's just coming out of the source, and power is a lot more concentrated in that wavefront per area, since it's such a small bubble in that time. So here you can see a sound source again, and the wavefronts here is basically chosen to be the points in the medium of full compression. So you see how the sound source keeps emitting these waves. So you have this periodic emitting of the wavefront here. And if you measure the distance between any two, you will get the wavelength, which you'll notice, by the way, that every wavefront in all directions is moving at the same speed. And the particles themselves obviously are not moving. They're just oscillating left and right, and they all oscillate with the same frequency. So because in the example of a spherical source, of a point source, you have this ever-increasing growing spherical wavefront coming out of it, the intensity drops off with the square of the distance from the source. So if you look at it, when the source is at a distance, let's say, equal to r, then any point in that wavefront there will have an intensity equal to I. When the wavefront has traveled twice the distance, now it's at 2r, then the area of the wavefront has increased by a factor of 4. So the intensity, because it's power over the area, will drop by 4. And once it goes to 3 times the distance it originally was at, 3r, now the total area of the wavefront is now 9 times what it was over here. So the intensity actually drops by a factor of 9. So you're standing here, you'll measure an intensity of sound equal to I. Over here, you'll feel a quarter of that intensity, and over here, 3 times the distance, you'll only hear a ninth of that. So that's why the farther away you are, the less loud waves seem. So quick quiz here, vibrating guitar string doesn't do much if it's not on the guitar body. And the question is, well, why does mounting on the body help? And if you go through the options, well, it's not that the string vibrates with more energy, because that's depends on, you plucking the string. So that that doesn't really change if you touch it to a guitar. You can pluck it the same way. Energy leaves the guitar more rapidly. This does make more sense because the vibrations of the string would pass on to the guitar, and being a bigger body, solid body, the waves will move through at a faster rate, and having a bigger area will mean that it's in contact with more air particles, so it will have an easier time transmitting its power through. The sound power is spread over a larger area at the listener's position. This is not really true because the power is spreads out as the wavefront spread out, but having a guitar with a string wouldn't affect the fanning out of the wavefront. It would still come out the same way effectively. The says the sound power is concentrated over a smaller area at the listener's position. Again, that's not true. And it says that the speed of sound is higher in the material of the guitar body. Again, so this could be true, but the biggest thing is that the guitar has a much bigger area than the string, so it's therefore in contact with more air particles, and as such, it delivers for the same intensity, it delivers more power because it has a bigger area. So it's B. Okay, so the way that we perceive sound, the way that we hear things being loud, is actually not just a function of how intense the sound is, how much energy is coming into our ears, but also the frequency of those waves. So the sounds that we can hear are a very, very, very wide range of intensities. And if you measure it with, again, in watts per meter squared, then you'll find that a lot of everyday sounds are magnitudes of 10 apart in intensity. So an alarm clock is like 1,000 times more intense than a whisper, and a jackhammer will be like 1,000,000 or more times louder than an alarm clock. So the scale here then seems like the sounds that we can hear bear an intensity in a logarithmic scale. And we don't really like comparing things logarithmically because it's a very, very big range. We'd rather work with a more sensible scale. Because, right, if I play two sounds to you and I ask you to rank them in a scale from 1 to 10 or a scale from 1 to 100, that'd be reasonable. But if I ask you to rank them in a scale from 1 to 1,000,000, you'd probably have a hard time, saying specifically, okay, how loud is 500,000? How loud is 1,000,000? So what we can do then is we can reduce the scale we're working with. We can work with a much narrower scale for discussing the sounds that we can hear by talking about sound level rather than intensity. So the sound level of a sound wave is just its intensity, but taking the logarithm of it times 10. So it converts intensity into decibels, and in doing so, it kind of rescales the intensity to a more linear scale. So in sound levels, an alarm clock compared to a whisper isn't 1,000 times more intense, but in sound levels, an alarm clock is only about 30 decibels louder. And the nice thing too about the sound level formula here is that it not only converts things to a linear scale by taking the log function, but divided by the intensity, you have this term here for the threshold of hearing, which is the lowest intensity that the human ear can react to. And with having this in the denominator, it basically ensures that at an intensity that's at the threshold, that's a sound level of 0. On the right, we have a few different sources of sound and what their sound level is. So again, note that the sound level basically is converting a logarithmic scale to a much more linear one. So rustling of leaves and a whisper are only 20 decibels apart, but in intensity, it will be about 1,000 times different in intensity. So with decibels, it's a much more sensible scale. So what happens if we increase the intensity of a sound by a factor of 100? What happens to the sound level? The rule of thumb, by the way, is that every time you increase the intensity by a factor of, say, 10, the sound level goes up by 10 for every factor. So if you increase the intensity by a factor of 1,000, that's 10 to the power of 3. That's basically 10 factors, 3 factors of 10. The sound level only goes up by 30 decibels. If the intensity drops by 10,000, so it drops by a factor of 10 to the 4, or in other words, it changes by 10 to the negative 4, then the sound level decreases by 40 decibels. In this case, we are increasing intensity by a factor of 100, which is 10 to the 2, so we'd expect to go up only by 20 decibels. If you look at the math, you have the sound level formula, and we know the intensity has now changed to be 100 times what it was. So with some log rules, we can actually take out that extra factor, and we take the log of 100, which is 2, plus the 10 in front gets us 20 more decibels at this sound level. So researchers have been able to find exactly what range of frequencies and sound levels create sound that the human ear can perceive. So perception of loudness isn't just, like I said, a function of intensity, but it's also a function of frequency. You can see that there's some low-level sounds in this region here that when the frequency is around 1,000, we can hear them. But if the frequency is too high or too low, we are not able to hear them. The threshold of hearing is a function of both sound level and frequency. However, no matter what the frequency is, as the sound level increases, you hit the threshold of pain where the human ear has a very, very painful physiological reaction to the sound waves. So anything past that is not a good time. In fact, a rock concert is right on the threshold. You can imagine that something like heavy metal will probably cause you some problems if you stand too close to the speakers. So the white area is everything that we can comfortably hear. Then the scale on the x-axis is frequency, which means that anything in this area is called a sonic frequency. And there's actually some overlap with the ultrasonic frequency region here in some cases if the sound level is high enough, somewhere on here. Bats emit ultrasonic waves, and you can see the red threshold here. And on the other side, you have the infrasonic waves, which thunder actually constitutes a combination of both infrasonic and sonic frequencies. Rifles, large rocket engines are very loud, which is why without proper ear protection, you could actually destroy your own ear cells, which is why if you ever seen pictures of the NASA engineers launching rockets or videos, you'll see that they're all wearing safety equipment to protect their hearing and also their vision. Well, that's all for today. I hope you join me next time where we will be discussing the Doppler effect and sonic booms.